Okay, good morning, everyone. Welcome to our presentation. This is Jeff Sampson, Alex Olson, and my name is Phil Neville. Our project today is to show you our tool, VIALAR. It is a water management tool. And as I begin to introduce our study area and what our tool exactly is, we're just going to show you a flyby of the study area and some of the water monitoring stations in the area. The lower Athabasca subbasin forms one of the world's most significant aquatic ecosystems. It hosts the Athabasca Delta, which has been designated a UNESCO World Heritage Site. This region also coincides with heavy industrial operations, resulting from Alberta's tar sands development. Alberta Environment and Parks collects data from monitoring stations in this region. However, they currently do not have any single platform to effectively view, query, and analyze this vast collection of hydrometric data. So that's where our tool comes in. Our tool is VIALAR, which means Visualize, Inform, and Alert for the lower Athabasca River. And it refers to a series of tools, both online and desktop, that enable visualization through the generation of graphs. We also support spatial proximity analysis with our networking analysis tool and also our distance to industrial areas, which we'll show you a little bit later. Our alert will display stations where chemistry levels have been breached. Chemistry levels are based on 16 different chemistry types that can affect the water quality. Our water quality limits or triggers are defined by the Surface Water Quality Management Framework, which is the Alberta government's commitment to monitoring and management of water quality in the lower Athabasca subbasin. Right, I'm just going to continue on here. All right, and I'd like to talk just briefly about our data. So most of our hydrology data comes from the Fisheries and Wildlife Management Information System, and that would be our rivers, lakes, ponds, any water types. And all of our chemistry data comes from the Regional Aquatics Monitoring Program, or RAMP. And this is a collection of 127 monitoring stations in the area, and where we get all of our chemistry data, or contaminants in the water. All right, and moving on. Just before I show my demo, I just wanted to mention some of the features of this tool, or the suite of tools. We've created a digital elevation model, a slope raster, a land use, land cover layers. And one of the key components, as I mentioned already, is this, the ability to visualize this vast assemblage of data and ultimately to help professionals make more informed decisions with water management. We have two methods of dynamic graphing for desktop and online. And I'm going to talk about the desktop version first. So for the desktop version, I'm going to show you three different tools. These were written in Python, and I leveraged Matplotlib and Pandas libraries for creating my graphs. All right, and I'm going to begin with our trigger tool. And this is our simplest tool, in a sense, where it'll just show one station and one chemistry type, and allow you to also see a trigger limit, so you would know if the levels are too high. And so with this tool, we select a Python toolbox, graph trigger. From this, I would select my station. Right? Every station has a unique identifier that we created. I would also select my chemistry type, examples aluminum, nitrate, ammonia, cadmium. After those are entered, the dates are automatically entered into our tool. All right? You would have a minimum and maximum dates, and those can be refined a little bit further. All right, I'm doing it a second time here. So as we said, we select our station ID. Then we select our chemistry type. All right, my date ranges are there. I'm going to select to show the trigger limit, and our resulting graph will show where the levels are exceeded. And as you can see, we can produce thousands of graphs very easily with this tool. Now, moving on, we have a similar tool. This is our station graphing tool. And this is similar to the first, except that now we can look at all of our chemistry types, or as many as we would like, for one particular station. For it to load up, all right. All right, and this is, these tools are meant to be used with the layers. I could zoom in, look for a station that I'm interested in, and from that I will open my tool, and the process is similar with the other. I will select my station ID, after I look at the help menu to help me. So I select my station ID. Now I have the option of including as many chemistry types as I would like. In this case, I'm going to select all chemistry levels. Date ranges, again, are automatically entered and can be refined by the user. And we get this graph showing all the 16 chemistry types or the available chemistry types for those stations. I'm going to show it again one more time. And what we have 16 chemistry types that vary in magnitude by about 8 or 9 significant figures. So the only way to successfully graph all of this would be on a logarithmic scale. So again, I'm selecting my ID, my station ID. I'm selecting all chemistry types this time. I'll leave my date ranges as they are. And output all chemistry levels for that station. And this would allow, say, a professional to examine different stations, to look for trends between stations. And getting into the idea of looking at trends, I'll show you our network graphing tool. And again, this is similar. This one also uses another tool that we created in Model Builder, our river routing tool. Which will allow the user to select start and end points and create a river network. So, get things going here. I'm just going to set my outputs. This tool is done in Model Builder. So I would zoom into my area of interest. And this will work for as short or as large of a network as you're needing to examine. So I select my start point, I select my end point. What this will do is it will select the river between those 2 points, but also it will select all of the stations. And we can adjust the tolerance to select more or less stations. Stations that may be too far off the river or maybe in a smaller river off can be excluded. So after my segment of river is selected, I can use my graphing tool, which looks similar with the other ones, where again, I'm just selecting this, the input stations that were selected from the networking tool. I'll select my chemistry type. Again, all my date ranges are automatically entered and can be refined. And I have a result now where each line represents a different station. So we can study the differences of station chemistry levels in a network, which would allow us to see possibly where a source of contamination could come from. All right. And now to speak about our land cover and land use, I will pass it off to Alex. Alex, go ahead.
Awesome, thank you, Phil. I'm Alex. Right, and I'm going to start talking, as Phil just mentioned, I'm going to talk about the land use and land cover map that we feel is necessary to create. And this is because this is great for spatial analysis. And in order to create such a map, we have to download some multispectral imagery, such as Landsat imagery, such as seen here. This imagery is rearranged in order to highlight the developed areas as seen in this kind of pinkish hue here. Right, then, the next thing we do here is that we created a Tasselcat transformation on the image. This type of transformation is a mathematical process that turns all the pixels into red ones that are developed areas, green ones that are natural and areas of trees, and blue areas that are water and moist areas. That's one of the rasters we created. But in order to further classify our image, we did a supervised classification. That means we manually digitize the polygons onto classes that we interpret ourselves. And these are known as regions of interest. We can input these regions of interest into an algorithm that outputs this raster right here. And as we can see, it's got oil sands, tailings ponds, and water, so it's all classified with us. So now we've got both our classified rasters. We can now create the end product, the land use map. Here it is in all its glory. Just a second here. So as we can see, we converted the polygons. And the rationale for that is because we can apply more geoprocessing tools that is in ArcMap. And because that is the reason that is useful is because we can do things like spatial joins, which can give us the distances each of these land use classes are to all the water quality stations. And why is this useful? Well, I'll show us here a hypothetical example. Station ALD1 has breached all of its triggers. We want to know why. We want to know what's going on. So what we do is, after applying the spatial join, our table, attributes table, tells us that there is a tailings pond that's 200 meters away and an oil sands tar pit that's 10 meters away. So is there some kind of tar sand contamination? Is there a leaky tailings pond? Let's just send out a field team just to see what's going on and maybe prevent further pollution from happening, because the Athabasca River is a really important water source. Now I'm going to pass it off to Jeff, who's going to show us the online functionality of our tool. Take it away, Jeff.
Thank you, Alex. Just a quick demo of our online web application. We tried to package all our tools that we just demoed here and bring that functionality online so GIS users and non-GIS users alike can access these tools.